Hello friends, welcome back to the lectures on Introduction to Statistical Hypothesis Testing. We are into the unit 3 now. In the first 2 units, we learnt all the theory that is required to take us forward to understand what is hypothesis testing. Now, we put together all of that and also recall the general procedure to understand the basics of hypothesis testing. In this lecture, what we will do is we will look at certain elementary concepts and learn the definitions of some key terminology in hypothesis testing, namely the type 1 errors, type 2 errors and significance level that one often gets to see in hypothesis testing. It is always a mystery for many as to what the significance level is. Some people confuse this for confidence intervals and confidence and so on. And then also one commonly encounters this notion of p value, we will also learn that, and mostly all of that through an example. And of course, what I will also show you now as the course proceeds, we will see how to do things in R. For example, we will see the definition of a type 1 error, mathematical definition or a statistical definition you can say, as well as learn how to compute a type 1 error in R. Right. So, it is going to be a mix of illustrations plus theoretical definitions. To recap the general procedure that we learnt in the motivation lecture, the first step in any hypothesis testing problem is to identify the parameters of interest, the parameters that really we want to test. And in any basic data analysis exercise, or even in this course, we are going to restrict ourselves simply to the first moment, which is average, second moment, which is the variability, essentially first and second moments of the PDF, or correlation if it is a bivariate analysis, or in a slightly more advanced situation, we are going to look at model parameters such as regression, parameters such as slope and intercept, and that is about it. In a more advanced situation, we actually look at other parameters. These are the parameters of the population that I have listed here: average, variability and correlation, so to speak of the truth. Once we have identified the parameters, obviously the next step, if you recall, is to state the null and the alternate hypothesis. Now, this requires some reading of the problem statement, because it varies from problem to problem, and it just takes a few practicing on a few different problems to learn how to formulate the null and alternate hypothesis. In this table, essentially I have listed all possible scenarios that one could encounter. So, if you take for example the null hypothesis, there are 3 possibilities: one of the equality type, like in the solid propellant burning rate example, or an at least type, where you say for example in a training method, maybe we would say that the training method is effective if the trainee scores at least some postulated or pre-specified value. Now, you should also notice that when it comes to testing the hypothesis is of the equality type. And if you recall, in the previous lecture, we went through a sample hypothesis testing exercise, where we got a feel of a hypothesis, and the procedure is, in order to test a hypothesis, we assume that the truth is what the null hypothesis states. That is, we anchor our results on the null hypothesis. Now, assuming that whatever has been postulated in the null hypothesis is correct, we compute the probability of obtaining the statistic as we have observed, or within the vicinity of what we have observed. And if that with that probability, if we find that the statistic falls in a high probability region, then we do not reject the null hypothesis. On the other hand, if the statistic falls in a low probability region, we reject the null hypothesis. Of course, we do make errors in both of this, and we will talk about that. But as far as the procedure is concerned, we anchor on the null hypothesis, and in order to anchor ourselves, we need an equality type, otherwise it becomes very difficult to compute the probabilities, because if I go by the statement at least or at most, then there are many possible truths which I have to test simultaneously, then it becomes very difficult. So, hypothesis test typically is conducted for one postulated truth, that is the bottom line to remember. And now, for the situation where I have at most, also I use the equality type. Now, at most could be, for example, in the automated filling machine example that we looked at in the motivation lecture, we said that we would accept the filling machine, or even the manufacturer would consider the filling machine as good if the variability in the filling across the bottles would be at most 0.01. Now, as far as alternate hypothesis is concerned, it is very easy. Once you have stated the null hypothesis, the alternate hypothesis is simply the complementary of it, so that the null and alternate together span the entire set of possibilities. For instance, if the null hypothesis is truly of the equality type, we are not talking about the practical null hypothesis that is always of the equality type. Practically all null hypothesis, as we have said, is of the equality type, but here we are saying the problem statement itself involves an equality type hypothesis. In such case, obviously the alternate hypothesis is of the type of unequal. We will not say inequality, but unequal, or that we say that the parameter is not equal to the postulated value. It could be to the left or to the right. Therefore, we call such a test as two-tailed or two-sided test, and I have a small thumbnail of a graphic that we will expand upon later on. I show you there, where you can see two small red regions indicated there. Those red regions are nothing but the critical values, and if the statistic, the observed statistic falls into this red region, it is kind of an alert region, then the null hypothesis is rejected. So, there is an acceptable region and the critical region, both computed as probabilities of the statistic taking on certain values, and this requires of course a knowledge of sampling distribution, as we have studied in the previous lecture. Now, of course, what I want to also add is that the schematic that I am showing you there, the thumbnail that I am showing you, is just illustrative. The curve looks symmetric, does not mean that the curve, which is the sampling distribution of the statistic, is always going to be symmetric. It is just to drive home the point of what a two-tailed test involves. It involves the testing of statistic to the left and the right of the postulated value, and you have critical regions on both sides. Now, when it comes to the other two situations, the critical regions are either to the left or to the right, depending on whether you are looking at a lower tailed or a left tailed test, or a right or an upper tailed test. In these two situations, the alternate hypothesis are strictly less than and strictly more than naturally, because the null hypothesis of an at least type and the alternate hypothesis should essentially complement the null hypothesis. So, the point is, when you are framing the null and alternate hypothesis, first look at the problem statement, and null hypothesis should always consist of the default. If nothing is stated as a null hypothesis, you ask, in the absence of data, what would be a de facto or a status quo or by default kind of statement, and then call that as a null hypothesis, and then whatever you want to test typically goes and sits into the alternate hypothesis. We will learn through a few examples on how to do that. And again, I want to emphasize what I have written at the bottom of the table. Although the problem statement may involve null hypothesis of inequality, like at least or at most, as far as the implementation is concerned, with the null and alternate hypothesis framed, and of course, the parameters of interest identified, the next step naturally is to choose the test statistic, which we denote by QT, and this test statistic, as I have explained earlier, can be thought of as a lens, that you are an inspector or you are a detective in search of evidence, and you are using this test statistic as a magnifying lens in search of evidence, either to reject H naught most of the times, but if you cannot find enough evidence, then you stick to the null hypothesis. In hypothesis testing, as we have learnt in the previous lecture, this test statistic is nothing but a mathematical function of the observations. It involves the estimate, and we have also talked about how to choose the statistic or how to choose the estimate that goes into the test statistic. It should satisfy the conditions of unbiasedness, efficiency and consistency. Sometimes robustness may be required depending on whether the data has outliers or not. And then once you have constructed the test statistic, you obviously need the knowledge of sampling distribution to compute the acceptable and the critical regions. That is, to compute the probability of obtaining a statistic as it has been observed, whether it falls into the then low probability region and high probability region. For this, we may need the probability density or the probability mass function, as the case may be, depending on whether the test statistic is a discrete valued random continuous valued random variable or a discrete valued random variable. Once we know the sampling distribution, then the only step that is left is to set the rejection criterion. That is, I compute the test statistic, and now I want to ask, if the null hypothesis is true, do I actually consider this value of test statistic that I have observed acceptable or not? For this, I have to set a certain threshold, that is what we call as a critical value. Now, this critical value can be specified in different ways. In an elementary way or a rudimentary way, you can directly specify the critical value. When we directly specify the critical value, it does mean something on the type 1 and type 2 errors that we will shortly learn, essentially the errors that we will make in hypothesis testing. On the other hand, in the second approach, we specify the amount of error that we are willing to tolerate in the hypothesis testing, from which we derive the critical value. It is a second approach that is widely followed, because then the user knows a priori what is the error that one will incur in the hypothesis test, vis-a-vis the first approach, in which the critical value is specified by the user based on some experience or intuition, and then the error has to be computed. We will go through both procedures here in this lecture. Once the critical value is decided using either of these approaches, the test statistic is compared with the critical value and determined whether the test statistic falls in the rejection region or the critical region or the acceptable region, and the decision is made. So, this is essentially the generic procedure that one sees in a hypothesis test. And this is nice because you can now apply this to any hypothesis test problem. What is important is to make sure that at every stage we have made a sound effort to choose, for example, the parameter or frame the null hypothesis or choosing the test statistic and determining sampling distribution and so on. Once we are sure about our effort and the choices at each stage, then the outcome of the hypothesis test is typically a reliable one. And now, having said all of that, we should keep reminding ourselves that every hypothesis test, no hypothesis test is perfect, let me put it that way. Every hypothesis test will incur some error, and that is where we talk of type 1 and type 2 errors, which we will understand shortly. So, let us do that. We will define type 1 and type 2 errors shortly, but before we do that, let us get a feel of what is this type 1 error through an illustrative example. And in this example, we go back to our favorite study of random number generator producing random numbers with 0 mean, like the R norm in R or maybe RANDN in MATLAB. So, the problem statement is as follows: a random number generator claims to produce random numbers from a population of 0 mean. There is no concern about distribution at this moment. From a population of 0 mean and unit variance. Let us assume that we have faith in the variance, that is, variance is unity. So, the only parameter of contention is the mean. Therefore, the goal is to test that the population has 0 mean with a known variance of 1. And the assumption that we will make is that we will now draw random samples from this population, and the sample size is large. Now, this large sample size is only because we are going to use a sample mean, and we know that the standardized sample mean follows a Gaussian standard Gaussian distribution regardless of the distribution of the population. If the distribution of the population is Gaussian, then we do not have to make this large sample size assumption. Now, in a stepwise fashion, the null hypothesis is obviously mean is 0 and the alternate hypothesis is that it is not, and the test statistic naturally based on our previous discussions is our standardized sample mean. And the rejection criterion now, what we can do is we can because it is a two-tailed test, you can if you recall from the previous discussion, we do not know if the observed statistic will fall to the right or to the left of the postulated value. Therefore, we need two critical values, one for the left and one for the right. We call that as Z subscript CL and CR for the left and right ones respectively. As I said earlier, there are two possible ways of specifying those. One, it can be a user specified thing. I can specify what the critical values are, saying that I know that for this kind of a process, this many samples, the probability that is that I will not observe a test statistic as large as ZCR or as low as ZCL, and then go ahead with my hypothesis test. Or the second approach where I specify the error that I will incur and then determine the critical values. Let us go through the first one, because that approach, because that tells us what is meant by type 1 error, and we will illustrate this in R. Of course, once we decide what the critical values are, then the decision is fairly easy to make. Let us now switch over to R. Maybe if you have not opened up R on your laptops, you can actually fire up R on your laptop and then walk with me through this example. All right. So, what I have done here is, in the interest of time, I have actually written a script that does this for us. Now, the purpose of this script is not just to perform the hypothesis test, but also to illustrate the concept of type 1 error. What is this type 1 error business? Before we go into the example, let me just give you some brief background on it. Remember, in a hypothesis test, we have a null and we have an alternate, and we make a decision whether the null should be rejected or not rejected. Now, obviously, there are different possibilities here. One of the possibilities is that the null hypothesis is true and I end up rejecting it, right. Indeed, for example, if the manufacturer claims that the solid propellant burning rate is on the average 50 centimeters per second, and I, as a quality inspector, depending on how I have collected, what is the variability and so on, end up rejecting it. Or in this example, random number generator, let us say the truth is that indeed the random number generator, for example R norm, does give me numbers from Gaussian distribution with 0 mean, and I end up rejecting that, maybe because I have such a realization that although I am sampling randomly, there is still a possibility, because I am choosing a critical value that can cause this rejection. That probability of rejecting the null hypothesis when it is true is what we call as type 1 error. So, let us go now through the example. Because I have to calculate the probability, that is the chances of making an error. What kind of an error? Rejecting the null hypothesis when it is true. I need to actually repeat this experiment of hypothesis testing for different set of samples, that is different samples, in other words different replicates or realizations, and then count the number of times I have made a wrong decision. We will assume that H naught is true, that is indeed R norm does give me numbers from 0 mean. So, what we shall do is the same thing that we did in a few other examples previously. We use a replicate command to repeat our experiment of drawing the numbers from this Gaussian population. So, if you look at it on the top, I have set the parameters of the simulation. R stands for the number of replicates, and n, small n, as you know, stands for the sample size, and then you have mu naught, which is 0. What is mu naught? It is a postulated value, and the mu true is the truth value, and we set that to 0 because we assume that R norm, in the sense if I do not specify anything in R norm, you know the default values are 0. There is nothing wrong in setting this to 1, but then later on I have to take this into account when I count the number of instances I go wrong. For the time being, we will reset this back to 0. So, the true mean is 0 and the true sigma is 1. These are the parameters of the or the settings of the simulation. Now, we generate the data and the statistics, and remember we are going to repeat this R, that is 1000 times, and therefore, we put through this mean calculation, data generation followed by mean calculation through the replicate. As I have said earlier, you could do this using a for loop, but this is lot more efficient, and the command syntax is fairly obvious. In the innermost operation, I am drawing 1000 samples randomly from a very large population that follows a Gaussian distribution of 0 mean and variance 1, and then I calculate the sample mean and I repeat this 1000 times, and that result is stored in mu underscore est. This is the unstandardized sample mean, but our test statistic is a standardized sample mean. So, in the next line, line number 9, I am actually calculating the standardized statistic, assuming that I know sigma, which anyway we have stated earlier. Now, just as a cross check, we have learnt earlier that the sample mean follows a Gaussian distribution. We have also seen that through the simulation. Just to reconfirm and reinforce these concepts, we can, if we wish, plot a histogram of the standardized test statistic, and one should expect a Gaussian distribution. We will see if that is the case when we run this source code. And finally, now we come to the focus of this script, which is to compute the number of instances I make a mistake when the truth is that mean is 0 for a specified critical value. So, now let us say because the Z, that is the standardized test statistic, follows a standard Gaussian distribution. We know from Gaussian distribution what kind of extreme values we can expect to see in a standardized Gaussian distribution, and critical values are something like extreme values. We are saying that the critical value is what you can obtain as an extreme thing when the null hypothesis holds. Of course, the true extreme values are minus infinity and plus infinity, but that is then covering all kinds of situations. No, we do not want that, because those values can be obtained also when the null hypothesis is not true. That is the point. We want to ask, if the null hypothesis were true, that means if the true mean were 0, what are the most likely values that I will get to see for the test statistic? And based on my understanding of the standard Gaussian distribution, I choose the left and right critical values to be -2 and +2. Well, that is my choice. I can even change it to -3 and 3 or -1 and 1, but because it is a Gaussian distribution, it is a symmetric distribution, the critical regions also have to be symmetric on either side of the postulated value. So, let us say I choose 2, and that is plus or minus 2 as the critical values. Now, in lines 18 and 19, I am counting the number of instances I would reject the null hypothesis when it is true. What is the criterion for rejection? If the observed statistic, that is the Z value, is outside this interval of -2 and 2, -2 and 2 inclusive, then the null hypothesis is rejected. That means, I am looking at the instances when the Z value is less than to the left, that is to the left of the left critical value, or more extreme than what I specify as the right critical value. And the sum here basically, this is a logical operation that I am performing. I am summing up all the number of ones. Whenever this is the case, the result of this logical operation is 1, otherwise it is 0. So, by summing up the result of this logical operation, I get a count on the number of instances I have made a mistake, and that is reported in some count, and probability is essentially the fraction of the instances that the total number of instances is a sample size itself. So, let us run this source code and see if I can calculate this. Let me actually clear all the variables in the workspace. I have done that. Let me run this, and what I see on the right is a figure which shows the histogram of the test statistic that I have computed from repeated experiments through the replicate, and it shows a Gaussian distribution. It comes as a no surprise, we know this already, and we can see that it is centered around mean 0. What is of interest to us is this probability of the error, that is the number of instances that I have made a mistake as a fraction of the total sample size. And you can see that this is roughly 0.05. In fact, if I run this again, I will get a different probability, slightly different probability. That is because you are dealing with a different set of 1000 realizations and so on. But the point is the probability of making a mistake, what kind of mistake? Rejecting H naught when it is true. That is saying that no, this random number generator is not giving me numbers from a mean 0, although it claims so, is very low. Rejecting that is very low, but there is a chance of rejecting it. That means you can end up with a realization when our stars are not aligned well, we can end up with a realization which will result in a rejection of the null hypothesis when it is true. This error we call as the type 1 error, and usually this is denoted by the Greek symbol alpha, and the significance level is also the name given to this type 1 error. What I would encourage you to do is play around with the critical values. For example, we could actually change the values from -2 and 2 to -3 and 3, and of course, make sure you save the file and before running the source, and of course, before asking whether the type 1 error will now decrease or increase, that is before running the source code, we can and you think of the answer before I run this code for you, whether you expect the type 1 error to increase or to decrease. Remember what we are doing by changing from plus or minus 2 to plus or minus 3, we are extending the acceptable range. We are allowing more and more possible values to be for the test statistic to be acceptable. So, let us run this now and see what probability we actually get. It is very low, that is compared to what we have seen for -2 and 2. In fact, now you should expect that as you extend the acceptable region, the type 1 error starts shrinking. Ideally, you may think, we may think that why not actually set the acceptable region to maybe -10, plus or minus 10, or even plus or minus 100, so that I do not make any errors at all in rejecting the null hypothesis. Well, life is not so easy. Once you try to minimize this type 1 error, there is some other error which will shoot up, and that is what we call as a type 2 error. And let us now go to the definition and see why this is so. What happens when we try to reduce a type 1 error? Where else are we really affecting the problem?